Hello everyone, good evening. So I would welcome you to the tutorial class on ME75, that is the foundation of CFD course. So today we will be mainly dealing with the tutorials on your week 5 content, that is the analysis of convection schemes and the pressure velocity coupling algorithms. So last week we had mainly dealt with a simple convection diffusion formulation, and then we had seen just how to solve these convection diffusion dominated equations, which are very common in our computational fluid dynamics. The momentum equation in fact is just a convection diffusion equation. So we had tried to take some ideas from the energy equation, that is the governing equation for temperature, and then we had tried to just solve a simple 2D temperature distribution equation, and we had written a simple code to solve that particular equation also last week. So, continuing with that particular analysis, in this week also we will mainly see the how we can analyze different convection schemes and why we have to uh, stick to a particular convection scheme when we have a given set of parameters. Like we will try to analyze these convection schemes for different conditions. That we will try to do using a simple code today. Okay, so then we will come to know which kind of schemes we have to use in which type of conditions. Okay, so that is the main agenda, that is point number one. The second point is then we will go on to our actual mass and momentum conservation equations for fluid dynamics. Okay, then we will try to see what are the main challenges which we face in this particular mass and momentum conservation solution. Okay, so and we will try to see how people have tried to overcome these challenges and like what is the current state of the art. So we will briefly touch upon the solution methodology for the Navier-Stokes equation, if I have to say it to the point. Okay, so we will try to see the solution methodology for Navier-Stokes equation, but today we will be not writing any codes for that particular Navier-Stokes equation. We will be we will be trying to write the code for your convection schemes, analysis of convection scheme. So first of all, just I would like to know whether I am audible or not. Okay, so I have just started. Can you write on the chat box whether I am audible or not? I just forgot to ask that. Can you guys write down on the chat box whether I am audible or not? I hope I am audible. If I am audible, please write yes. Okay, okay. Thank you, Ayaz. Huh? Okay. Yeah. So what I was discussing is that so today we will be mainly looking into the week 5 contents, the tutorials on that. But mainly we will be touching upon a code. We will write a code to see the behavior of different convection schemes. Okay. So given some conditions, which convection scheme would be better? So to test that, we will write a code. Okay. In your weekly content, this was also present, but it was present in the form of your AP, AW values were given, and then directly I think the solution was given. Okay, so we will use that and write a code and then just see practically. Okay, so that is the main agenda. Okay, apart from that, we will solve some questions, second part, and then in the last part we will also see which are the different algorithms to solve the Navier-Stokes equation. Okay, that is the main I would say the holy crux of your CFD. Okay, but we will not be writing code for Navier-Stokes today. That we will try to see it in the next week. Okay, So just let me give a brief recap. As I said, so my screen is visible, right? I mean, I have shared the screen. Is the screen visible? Can you write on the chat box whether my screen is visible or not? My screen is not visible. Okay, just hang on. Okay, it is visible to Siva, but not visible to Ayas. Why? I'll just stop sharing and then maybe reshare. Yeah, is it visible now? I think it should be visible. Yeah, now visible. Okay, okay, thank you. Hmm? Yeah, so what I was saying is that first we will try to see the performance of different convection schemes. So that is one thing, and then we will also write a code in between. So today I have kind of changed my schedule a bit. So first we will just see this convection scheme, and then we will write a code first. Okay, instead of doing that in the last part, we will first write a code, and then we will try to go into some tutorial problems. Okay, so that is what I have thought for today. Okay, so the second thing is which I missed out is the time advancement. So how do you advance in time when you are solving an unsteady equation? And in most of the CFD problems, you will be solving unsteady problems only. So you have to march in time, and what are the methods which are available and which methods are more accurate, kind of things. Okay, that also you have studied mainly in the week 4. And then the pressure velocity coupling, which I just now discussed. Okay, so the first thing which you have to remember, not remember, just understand, is that your convection diffusion equation is very common, and mainly it is encountered in the momentum equation of your CFD, and in general it can be written in integral form, just as the as one advection term and the diffusion term. Okay, usually it is called as convection also, but there is actually a fine difference between okay, your advection and convection. Anyways, so then it is written, this is the your convection part, so you should know only this. Okay, then you have the grad of rho divergence phi. Okay, these are volume integral only, both dv. Okay, now this is what you have to know. Apart from that, in your weekly content you have the values for AW, AP and all for different schemes. You need not remember those things. Okay, if you remember, then you will definitely get confused with those. Okay, so just you have to understand this equation. I mean, when you practice, I mean, this equation you will kind of get to know very easily. Okay, and this is a steady part. We have kind of ignored the unsteady component. Okay, dou phi by dou t here. Okay, we have set it to 0 because we are solving for steady equation. Okay, so now when you kind of okay, here I think rho will also come. Okay, so when you kind of perform the Gauss divergence theorem, apply the Gauss divergence theorem, you can convert this volume integral into the surface area, the area integral. Okay, so then when you integrate this on just say just a 1D control volume, which we have anyway discussed. Okay, with this as the P, the centroid of the control volume, and west and east phase. And let me remind you that we are all trying to solve this with the finite volume framework. Okay, so we have this control volume where we have west phase and east phase. Okay, so mainly what you will get is this. Okay, what you will get is rho u into phi, okay, on east minus west is equal to your tau into divergence of phi, again east minus west. Okay, I have ignored a also here. Okay, I am assuming ae equal to aw, so that is why I have kind of ignored the a also. I have cancelled it out. Okay, so tau divergence of phi at west face. Okay, so mainly all the terms are quite clear here, that the divergence of this phi you will calculate this as phi of at the east face, say you will calculate it as phi capital E minus phi p divided by delta x, and all those things you already know that we have done in the last week also. Okay, the only thing, the only challenge here is with respect to calculation of phi at e. I mean, you know the velocity also at e, assuming that. Okay, so phi, the variable phi of interest, that at the east face. Okay, that you have to determine very in a very sensitive way, I would say. And why, that I have explained in the last week also, by giving just an example of a person who is standing in between fire and in between and ice. Okay, when there is no flow, what happens, and when there is some wind speed, what happens. So that is the importance. So why we have to be careful while calculating this phi e. Now we saw that there are upwind schemes, okay, in the last week. Okay, so like phi at e, you can directly write it as, say, um, phi at p using the first order upwind scheme. This is the upstream direction. Okay, this is actually phi at capital U, the upstream, which is nothing but phi at p, assuming that the flow is in the positive x direction. Okay, so similarly we had second order upwind scheme, and then in the current week we mainly dealt with what is known as quick scheme. Okay, a quick scheme was kind of introduced to a larger extent in this weekly content, and then we finally set to see which of the convection scheme kind of gave us a better answer as compared to the analytical solution. So there was a mainly a problem through which we had analyzed the different convection schemes. So that problem was something like this: you had a like a 1D, say, domain. Although this 1D might feel like very hypothetical kind of situation, many a times what happens is that in the second and third dimension, uh, the distances, the dimensions, they are very long, and so sometimes 1D approximation can also work. Okay, so this is like a simple 1D domain which I have drawn here. Okay, the problem which you had, I think it was like phi is equal to 0 and it is going to phi is equal to 1 at the right end. Okay, the value of phi, these are the boundary conditions, and we have to solve for the values of this variable phi at different points in this domain. So assume this, take it like say velocity or say temperature. Okay, assuming this to be temperature just to get a realistic sense. Okay, so temperature is 0, temperature is 1 degree Celsius here, how the temperature varies. So that we have to see. But again, now the problem here is that we are given the velocities. Okay, I think we were given two velocities, like one case considered a very low velocity and the other case considered a very high velocity. So in these two cases, which of the convection schemes will give us the better results? So that we had tried to see. Okay, in the weekly content, I think that just the direct answers and the comparisons with analytical solution were given. So what we will try to do is we will try to write a code for this today, and then we will try to see the answers. Okay, so I'll just explain step by step how we can write a code and analyze practically which of the schemes would be better. Okay, so the The major difference which you will see in my code today is that I will be doing it for unsteady convection diffusion, okay, not a steady state. Ultimately it reaches the steady state, okay, so that's a different thing. But always I usually try to do the things using an unsteady formulation, because it kind of is easy to code, okay, and it is kind of easy to understand for you people also, okay. Because what happens in a study, if you are trying to solve a steady state equation, is that you will have to calculate aw, ae, ap, those terms, okay, first, and then write the code accordingly, and then do the Gauss Seidel iteration and all, okay. So those things will be necessary when you are trying to do a study kind of solution, which we did anyways in the last week. But unsteady things, they are very easy to understand, okay, the unsteady codes to write and to understand as well, uh, because you people have to understand it, right? So it is easy to understand also, and it is easy to modify also. That how it is easy to modify, that also we will see today, okay, the code, the coding aspect. So and all the real life situations, they are unsteady only, okay. So it is better to write an unsteady code, that is my opinion, okay. The only thing, the advantage with the steady state solution is that you will get very quick results, okay. So computational cost is very low for the steady state solutions. But a generalized code is always an unsteady state this thing, okay. So mainly I'll be trying to solve this particular kind of equation, that is your dou phi by dou t, and anyway rho is 1, okay, in your that equation, and this thing also. So I'll just ignore the rho also here, okay. U into, sorry, divergence of phi, okay. So this is your equation, which is equal to tau into del square phi, okay. If I assume tau as constant, then I can bring it outside also, okay. I'll be trying to solve this. Now you can see that it becomes very easy in a discretized manner, with a say explicit time stepping, okay. I can just write phi n plus 1 is equal to phi n plus delta t, okay, into this minus of, if I do the finite volume integral of this, what I'll get is u into phi, right, at east, minus u into phi at west, okay. If I do the finite volume integration, okay, and then what terms will be remaining, minus of this plus the diffusion term, okay. So diffusion term, how we will write, tau into this thing, whatever is there, the del square phi term. So that you will get it as del phi term, okay. uh, d phi by dx at east, minus d phi by dx at the west face. Now you will again apply this thing, okay, here, what do you say, the first order difference, forward difference, okay. So that you will apply for this, you know, that phi into capital E minus phi of capital P divided by delta x, so that anyway you know very well. So anyway, that I will not discuss, okay. So this is the whole thing, okay, and let me put the bracket here. So this is the simple code, okay, and all these things are at nth time step, at all at n, because I am doing explicit time marching. If I would have done implicit, I would have put n plus 1, okay. So that is the difference, okay. So any questions till this point? So now I will start showing you the code, I mean part by part, okay. Are there any queries till this point? Okay, if there are no queries, I'll just jump in into the code, okay. Okay, so the first thing, as I always say, is to kind of initialize the variables. Okay, whatever variables we have in this question, so that I am writing it down first here. Okay, so like for example, the number of grids in the x direction, length in the x direction. That we have 1D domain. Okay, it's only the x direction, anyways. And then I am calculating the del x value and the delta t value. Okay, and then the value of row, and based on this I am calculating the Peclet number also. Okay, why I will explain it. Okay, maybe I have not calculated it accurately correctly here. It should be del x, not. Okay, it should be del x. Okay, and then whatever it is, other things are not much needed. So you need only the density, which is set to 1, and I think mu I had taken 1 by diffusivity. It's just with respect to the momentum equation. And in your weekly content it might be different. Just see this. Anyways, I just wanted to check the effectiveness of using different convective conditions. And then I have just taken two schemes here, first order upwind and the central difference scheme for your convection. So I have defined kind of two variables, two initial conditions. So phi FOU corresponds to the phi calculated using FOU, whereas phi CD corresponds to the phi calculated, the variable phi calculated using central difference. I will also add now quick also, but first let us see for FOU and central difference. Okay, now the second thing is, after doing the initial conditions we have to put the boundary conditions also, right? So as I said, at x equal to 0 it is 0, and at x equal to 1, which corresponds to the grid point nx, okay, the last grid point, the value is 1. So 0 to 1 it is varying. Okay, okay. So these are all the pre-processing steps in your code. So these are usually called. And then I am calculating the analytical solution. Analytical solution equation also I think was given. It is an exponential relation. The phi analytical is equal to phi analytical at 0th grid point plus delta phi, that is the phi analytical at nx minus phi analytical at 1. This is actually the boundary condition. We already know what is the value at first and the next grid point. Anyway, that comes from the boundary condition, and then this exponential relation. Okay, okay. I think in this Peclet number, I think it was x, total length was included, I think. So that is why I had written L here. Okay, but it is strictly not L, it is del x. But in this I think the way in which they had defined, they had in the analytical solution I think L had come into picture, something like that. So that is why it's L, that is why I had included. Okay, uh, because initially I took del x only, but then I saw that in the relation it was L was there. It was actually rho u, del x into rho u, something like that. Something, it was like that. Yeah, I think it comes same only. If you see del x into PE by L, then it is actually our Peclet number only. That is what I think. Okay, but anyways, we'll keep it like this only. I had copied this from the your weekly content, this thing, analytical solution which was given there. Okay, okay, fine. So this is all the pre-processing which we have to do. Any queries with respect to this pre-processing? So what we have done, we have just defined the parameters, our in whatever was given in the question. Okay, so these might values might be slightly different. Okay, just hang on. Okay, so and then we have kind of set up the initial conditions. Just I have given once. You can also give 0 also. That's not an issue. Okay, and then the boundary conditions I have set up. Okay, at left end and it is 0, at the right end it is 1, and FOU and CD, two things I have taken here. Then analytical. Okay, are you following this code? Can you write down on the chat box? Okay, thank you. Okay, so this was all pre-processing. Now I'll just enter into the time marching. As I said, I am solving unsteady equation, huh? Okay, instead of steady state, because it is just easy to understand. Okay, that's the only motive. Okay, uh, I'm just starting with the time marching now. Okay, so as I said, we have n plus 1 and n. Okay, this old means n at the nth time step, and phi FOU is what we are calculating, that is at n plus 1. This is n plus 1. Phi old means n. Okay, I'll just maybe write it here. Old implies n. Okay, otherwise if there is no old, it is n plus 1. Else n plus 1. Okay. So time I am incrementing and iteration count also. Okay, I'm just updating the things here. Okay, sorry, I think I missed to put this part. Okay, while, so I'm just stopping at some time. Okay, you can also do that maximum error thing which I did last week. You can try to see when we get the convergence and then stop it when we get convergence. But in unsteady state solution we usually stop at particular time. Okay, when we know that we will get the periodic solution, uh, because we will never get a steady state solution for an unsteady state problem. Okay, it's the solution is always periodic. It's like a sinusoidal curve. The equations, the results are always sinusoidal in nature. So with respect to time they will not always come to a constant value. Okay, this that happens only for steady state problems. So I have generalized the code here, so I have kept it unsteady state, and I am trying to end it at some certain time instant. Okay, okay, this is anyway the updation. Okay, this is in technical term it is called updation of the variables. Okay, updation in time. Okay, and then now everything lies in this whole part here. Okay, okay, so what I have done here is that I have calculated phi at east using FOU scheme and using central difference scheme. That is why I have given two variables, central difference and FOU. Okay, now you can clearly see that it is very easy to understand. Why I was telling it is easy to understand, it is easy to understand is because why is it easy to understand is because I have just directly written phi at east, okay, is equal to phi at I for a FOU scheme, because my velocity is in positive direction. Okay, so just let me try to explain that. Okay, so this is the our centroid of the control volume. Okay, so this is the west face, so this is the east face. Okay, this grid point will be capital W and this will be your capital E. Okay, so I am trying to calculate the phi at E. Okay, now phi at E according to the FOU scheme will be phi at upstream point. Now since the velocity is in positive x direction, u is equal to 1 I have written, I think. So upstream will be nothing but phi at P. Okay, so that is what I have written, phi old FOU of I. Okay, this is very easy to understand, right? Like now similarly phi W at the west face. Okay, now at the west face if I want phi W here. Okay, now this is again equal to phi of upstream. Upstream for this will be phi of capital W. Okay, now which is nothing but phi old of FOU at I minus 1, because remember I am doing what you say explicit time stepping, so I am taking n. Now n means old, right? I have written here old implies n, so that is why phi old FOU of I minus 1. So similarly I am doing for central difference scheme. Okay, so central difference you do not worry, it will be very easy. Okay, whatever is the value of u doesn't matter. Phi e will be calculated using the average of this phi p and phi e. Okay, whereas the phi west will be calculated as the average of phi capital W and phi capital P. Okay, so that anyways I have written it here. Okay, I and I minus 1 will give me phi W, and I and I plus 1 will give me phi at east face. Okay, so this is it. Okay, so this is the whole thing. Then I have just written whatever I had written it here. Okay, phi at east, phi at west, I have calculated it. So now you can see that it is very easy to understand. Okay, so just phi at east, phi at west, dou phi by dou x, anyway you know that at the east face it will be phi at capital E minus phi at capital P divided by del x. Okay, so that is what I have written, and then finally what I am doing here, unsteadiness, anyway I don't need this. I'm just plotting the values. Okay, okay, so this is for this. So you can just see now how it will behave. I think it will take some time because it is unsteady solution. As I told, unsteady solutions usually tend to take some amount of time to run them. Okay, so now you can just see that I need not require calculating AW, AP, okay, those things which are a bit complicated. I mean, you have to do this in paper and then just do this. So otherwise, this is a very simple thing of coding. Okay, so now you can see what is happening is that I had taken, I think, how many 11 grid points here. Okay, with a velocity of 1. Okay, it's like your 2.5 case, I think. In I think there it was 2.5 or something in the weak contents. So what you can see clearly with this code, what it is doing. Now I think the analytical one is this particular curve. I think you can see it a bit. What do you say? uh, okay, so this is your analytical. Okay, sorry. Okay, so this is your analytical one. I think it is denoted by this orange color or something like that. Okay, so here you have got the legend also. So it is directly going from this 0 to 1. Okay, when x reaches 1. Okay, it's just a direct jump which is happening. Okay, and then you can see your red color curve, this one. I think my pointer is visible. Okay, so this particular thing curve, so this is your FOU. Yeah, it is FOU. It is giving a bit closer result to the analytical one. Okay, at least the trend is okay, I would say, uh, because you are getting a kind of start from 0 and slowly exponentially increase to 1. Okay, so that trend you are getting. But this blue color curve, that is for your central difference. Okay, central difference, you can see that it is wiggling, it is giving a zigzag solution. Okay, which is very much not needed, I mean, which is not good. Okay, so you can clearly see that central difference scheme, which is not an upwind scheme, is kind of giving you a very bad result. This is not expected typically. Okay. Um, Now, why do you think this happened with this kind of conditions which I have written here? Can you write on the chat box? I mean, this was, I think, discussed in the weekly content also, but anyway, just I'm asking this question. Why are you not getting a good solution with the central difference scheme? Can you write on the chat box? I think this was discussed in the weekly content also. Like when you have a very high velocity, what will happen? There, I think it was 2.5 or something like that, as far as I remember. U is equal to 2.5 was there, and I think the grid points were 5 or something. N is equal to 5. There was a case. This is also similar, with, just with 1, and I have taken 11 grid points. So what we are observing is that the central difference is not giving a good result. Okay. Okay, I don't see any answers on the chat box. Anyway, so the main reason is because of the ratio of this convective to diffusive force. The convective force is quite high as compared to the diffusive force. Okay, or you can say diffusive flux and convective flux. When the convection is very high, then you can't use this linear interpolation. The logic I had explained last week also. I had given a very simple example. If a person who is standing between fire and ice, and if there is a very high velocity, then the direction of the velocity will influence the temperature which he feels. Okay, so that I had explained last week also. Similar logic that is itself indicated by the ratio of this convective and diffusive fluxes. Okay, so that itself is called as Peclet number, and whenever you have a high Peclet number, which is true for this case, because if you can see, the diffusive flux is kind of defined by tau. Okay, and I have set it to 0.02 here. Okay, so it is very low, and then the convective flux is kind of defined by your velocity 1. So you can say rho into u into delta x divided by mu. Okay, so what will that turn out to be? Okay, so think 1 into 1 into 1 divided by 10 divided by tau, your mu here in this case 0.02. Okay, I think this will be 50. 50 by 10 is 5. Okay, which is very much greater than 2, your threshold level. Okay, so anyway you have to use a good appoint scheme here. But now what will happen if I kind of do this by 100, or say, okay, let us consider 100, or else let us consider 50. Okay, let us not consider 100 for just for ease of calculation. One, if I do it with a 50 grid, what will happen now? 1 upon 0.02, this will be 50 divided by 50, it will become 1. Okay, so here you can kind of use a central difference scheme now, because you can see that the Peclet number is going less than 2. Okay, so that is what I will do here now. Okay, I will increase the grid from 11, I will try to go to 51. I don't know, it might take a lot of time. Let us see. Oh, it kind of gave good answer. Okay, yeah, so now you can see very clearly uh, that all of them are giving good results to me. This blue color is the central difference, and actually uh, even then the first order appoint is kind of more close to the analytical one, but now the central difference is not giving me that zigzag solution which I had obtained last time. Okay, so now the central difference is also kind of giving me good results. Why? Because I have taken more grid points and I have reduced the Peclet number. Okay, so that's the whole game here. I hope you can understand this. So in your real life situation, in the practical cases which you solve, you should first try to see which convection scheme I have to use. uh, See, these things are all, I mean, these things depend on many factors. Okay, many a times even I do use central difference scheme only. Why? Because the central difference scheme, although you might feel that it was giving zigzag results and all, sometimes if this Peclet number, if you are reducing it, central difference kind of is a very stable scheme, and it gives I mean, it gives good results and it is stable. Okay, but only thing is you cannot use it at some instances. So you have to just check what case you are solving, and based on that you have to select. I mean, given a choice, I would really go for a central difference only. That is what my experience has been. Okay, but really in many practical situations you will get into some upwinding scheme. You will have to get into some upwinding schemes because the flow velocities are very large. Okay, and in those scheme and in those conditions you have to go for FOU or SOU or even a quick scheme. But be very careful with quick scheme. As I told last week also, it is quite unstable. I mean, you have to handle it very carefully. Okay, so that's the only thing. Otherwise, second order upwind also I have seen that kind of gives me good results. Okay, so that is what my experience has been. Okay, so I hope that you have kind of understood something from this small coding exercise which we did. Okay, so anyway, I'll be sharing these codes with you. You can just go through them again, and if you have any queries also you can contact me, okay, later on. Okay, any queries with respect to this code? I mean, I just want to know how you are feeling about this coding, this thing, what do you say, tutorials. Are you, I mean, understanding, are you following up with what I am really doing here, the coding part? I mean, I don't expect you to, I mean, understand the full code, at least the step by step procedure of how to write them. Okay. Yeah. Any comments on that? Okay, so what we have done is just we have got a brief recap of your week 5 contents now, and then we have solved a code, we have written a code and tried to see the results for different conditions, different Peckley number conditions, and tried to see which of the convective schemes are perform better, and based on this understanding we can solve the real life practical problems, okay, in future. And also that is one thing. The other thing which is more important is through these exercises you should be more confident with respect to writing codes. That is what I just hope. Like we have done like now three I think coding sessions. The first I think we had just solved a 1D diffusion equation, if I remember properly, and in the second session I think we had done a 2D or diffusion again, but a 2D one, and that with respect to finite volume method. In the first one I think we had just done finite difference. Again today we have seen a much more involved problem which involves convection also, and that is one thing. The second thing is which convection scheme to use. Okay, so those are the two aspects which we learned today. Okay, now these are like the tools. Okay, so whenever you have to kind of build something, you need tools, right? For example, if you want to kind of uh, say build a car or something like that, you need some cutting machines, welding machines, or something like that. Okay, some instruments you will be needing. So these are like those instruments. So solving this convection diffusion equation, okay, these are the tools with which you have to first get acquainted. Once you get acquainted with these tools, only then you can solve the actual Navier-Stokes equation. Otherwise, if you directly jump into solving the direct Navier-Stokes equation, writing the code, then you will end up with trouble. Okay, so that is what I feel. So first you should start practicing with this. Okay, so today I have kind of say I have taken a different set of parameters altogether here, which is different from your what you say weekly content. Okay, so what you can do is that you can take this code itself. Okay, take this code. I'll be uploading this code, okay, on the Google Drive. You set the parameters to whatever was there in the weekly content, and apart from first order upwind and the central difference, you people should also include phi quick. Okay, phi quick, that also you have to include. Okay, what change you have to make there? Okay, it is very easy now phi e of fou, phi w of fou, you have to just copy paste this, and then just make this instead of fou, write it quick. Okay, then you have to write appropriately this equation. Okay, this equation I will leave it. Okay, now I will just write it, what it will be. I mean you can look to the slides. Okay, of your weekly content. I think it will be 3 by 8 of t of upstream. Okay, whatever your upstream is there. um, sorry, 3 by 8 of, I think, downstream value. Okay, for this it will be T of E. Okay, I mean phi of E. Phi of into phi of I plus 1. East means I plus 1. No? Plus again you will get, I think, I don't remember. Uh, 6 by 8, 1 by 8. Okay. 6 by 8. You need not remember these things. Okay. You can derive these things and then write this. Okay. Phi of, you will get here now, you will get upstream. Okay. This is, I think this was downstream, upstream, and upstream of upstream. Yeah. Phi of I minus, and this all these things should, I think, add up to 1 or something. So it should be, I think, 3 plus 6 9, 1 by 8, 1 by 8 of phi of I minus 1. Yeah, this should be correct. Yeah, so like this you can write this thing. Okay, similarly write phi w of quick. So you now you can see that it's very easy to change this code. Okay. Yeah, so you have to make this appropriately. I think this will be just I, or what, I don't know, I minus 1 and I minus 2 you will get. So this is how you just implement this, and then just change phi E of FOU to quick. Okay, so this is how you do the changes. I will leave it to you as a kind of takeaway assignment. Okay, through this you can kind of learn the things in a much better way. I'll just comment it out. You can just uncomment it and do the changes as per the requirement. Okay, I'll just comment this also. Okay, so that would be the way in which you would, I mean, learn. That is what I feel. Anyway, it's left to you, and these are completely optional, anyways. Okay. Okay, so this was about the whole coding things. Okay, so just let us close this. Um, the last aspect which I would like to discuss before going into your problems is uh, the pressure velocity coupling, which I discussed, I mean, which I just told as just a recap. Okay, so yeah, so this was, as I said, all your convection diffusion equation. These are like the basic tools. Okay, now let us get into actual computational fluid dynamics equations, and let us see what are the equations, and let us see what are the challenges which you would face to obtain the solution for that. Now here, till here we were just solving simple equation wherein it is a non-coupled system. I would say uncoupled system, because you were trying to solve for phi. You already knew what was velocity. Okay, it's like phi is like your temperature. You already knew what was the velocity. You are solving for temperature. Okay, now when you come to actual computational fluid dynamics, things are unknown, all the variables are unknown. So if I just say only fluid dynamics equation, I would get the velocity, and if I take a two-dimensional domain, okay, x velocity, y velocity, and I would get pressure. Okay, these are the variables of interest. Okay, now very interesting thing is that we have three equations also. We have one mass conservation and two momentum. Okay, we have two momentum equation for two-dimensional case. Okay, so mainly we have three equations and three unknowns. It should be very easy to solve, and we might feel like that, but it is very difficult. There are many challenges in this solving this. So I would like to know from you, what do you know about these challenges? Can you write down on the chat box what are the main challenges in solving this mass and momentum conservation to obtain these variables? What are the main challenges? Can you write on the chat box? Non-linearity Yes, pressure and velocity are coupled. Yes, exactly. These two things are biggest challenges in computational fluid dynamics: non-linearity and the coupled equations. Okay, there is one more challenge. Anyway, I will discuss it later. Okay, but as you people have already quite correctly said that the momentum equation is a non-linear equation, because we get u, say in the x momentum equation we get u into dou u by dou x, okay, plus v into dou u by dou y, the advection term. Okay, so this is a non-linear term. In the diffusion, you don't get non-linear term. Only in this advection you get non-linear term. Okay. In the temperature, whereas you had okay, kind of u into dou t by dou x. If that is also in a sense non-linear because you don't know u. But at least when you knew u, it would have not been non-linear. But here it becomes non-linear now. Okay. So that is one biggest challenge. The second thing which is very interesting is, although I have three equations and three unknowns, there is a coupling between the pressure and velocity. Now what do I mean by coupling between the pressure and velocity is that in the momentum equations, in the mass conservation equation, I have only velocity terms. Okay, divergence of this velocity is equal to 0, whereas in the momentum I have the unsteady term, the advection term, but it also kind of depends on the pressure gradient also. Okay, now this pressure at say n plus 1th time step, okay, at the current time step will drive the velocity. Okay, and the velocity in turn will change the pressure. Okay, so they are kind of coupled in a two-way, so that is called two-way coupling. Okay, so both of them kind of influence each other, so they are highly coupled equations. Now the main challenge here is that pressure velocity coupling is there, but the main challenge is you do not have an explicit equation for pressure. Okay, now like for example you have dou u by dou t through which I can find u at n plus 1, right? U at n plus 1 is equal to, I can write u at n plus delta t by so on so, but here I have dou p by dou x anyway. If I had an explicit equation for pressure, I would have calculated that and then substituted it here, and then I would have directly calculated u. But we do not have an explicit equation for pressure. That is the I would say the biggest challenge, that we do not have an explicit equation for pressure apart from non-linearity. Okay, because the equations are coupled. Okay, so apart from these things, the biggest challenge when it comes to CFD is the pressure velocity decoupling when we use a standard grid. Okay, so what do I mean by standard grid? Standard grid is the one which we were using till now. Okay, wherein if this is our domain of interest, we kind of divide it equally. Okay, equally or unequally, whatever you want to say, and then at the centroid of this control volume we store the variable of interest. Okay, now if we do this same procedure, okay, for CFD also, what will happen? And if you are not doing any modifications, so what will happen if we are following this procedure? Can you write down on the chat box? I am storing all the variables at the centroid of this control volume only, and if I try to do the solution, what might happen? Although this will not happen in every cases, only in some cases the problem will arise. So I want to know what is that problem which you will get. Can you write down on the chat box? I think this was there in the weekly content, but Can anyone write down what issue you will face when you store all this at this centroid only? U and P at the same location. Yeah, so if I do that, what would happen? So as I said, that particular the thing which will happen, it is called as pressure velocity decoupling. It is called like that. So we have to understand why it is called pressure velocity decoupling. Okay, you already told that pressure and velocity are coupled, but if we kind of go with this approach, pressure and velocity will be decoupled. Okay, so we will try to see how that happens. Okay, so just let me consider a single 1D control volume here. This as P and this as E and this as W. Okay. Now in the momentum equation for UP, capital P, capital P. Okay, UP at n plus 1, I will be having dou P by dou X, right? So what I will get is dou P by dou X at the east face minus dou P by dou X at the west face. Okay, so right, I mean when you do the kind of what do you say, uh, discretization. So what you will end up with is PE minus PP plus PP minus P at W, capital W, huh? Okay, so what will happen here is that because this is dou P by dou X at E and this is dou P by dou X at W, okay, so ultimately this minus PP and plus PP, they will get cancelled out, and then you will be ultimately left out with capital PE and capital PW. So you can clearly see now is that the velocity at the pth control volume uh, doesn't depend on the pressure at the pth control volume. Okay, that is called as pressure velocity decoupling. Okay, now before we said pressure and velocity are coupled, but now we see that the velocity at the pth control volume does not depend on the pressure at the pth control volume. That is why we say it is pressure velocity decoupling. Okay, because now there is no dependence. Okay, so that is the whole thing. Now what will this create, why will this create a problem? So we have understood what is pressure velocity decoupling. Why pressure velocity decoupling is a problem? There is only one case where this might create a problem: when you have a very sinusoidal oscillation in pressure, especially when you are doing duct acoustics or duct flow. So you will have the fluctuation in the pressure. Okay, so what will happen is that so for example, here you might have 100 pascal, here you might have 50 pascal pressure, and here again at the east control volume you have 100 pascal pressure. Okay, this might happen in some cases only. Okay, now you can see here is that PE minus PW you will get, which is nothing but 100 minus 100, you will get 0. So there is no pressure gradient force which is driving the velocity uh, according to our CFD discretization, but it is completely false, because you can clearly see that the variation is something like this. So you definitely have a gradient in pressure, okay, which will drive the flow. So with such things you will get unphysical results, because ultimately you will get zero pressure gradient, which is not physically correct. Okay, so that is why the pressure velocity decoupling will create a problem. Okay, will create unphysical results, can create unphysical results. Why we have tried to see using this example here. Okay, and this is usually called in technical terms as checkerboarding problem, because the this pressure values are arranged like this. Okay, so people call it like that. Anyways, we will not get into that. So this is the whole problem. So is this understood? Are these challenges understood? Any queries in these challenges? please let me know, okay, on the chat box. Okay, so if there are no queries, so people have come up with uh, solution strategies to tackle these challenges, okay, which we will slowly get into in the from the next week actually. But just to introduce, I think some of the algorithms were given in this week's content only, but I think they will be continued in the next week content in detail, okay, and then we will try to write a code for to tackle these situations. But let us first get sorted with this, that these are the challenges, let us keep them in mind. And yeah, people have come up with various algorithms to tackle this. So the one of the very simple straightforward strategy to avoid this pressure velocity decoupling and the checkerboarding problem is to arrange the velocities, pressure at different locations in a control volume, that is called your staggered grid, okay, so that you are arranging the x velocity at this vertical line and the y velocity at this horizontal line, whereas the scalar variables, the pressure, temperature, whatever it is, centroid of the center control volume only you are storing it. So through this way you can easily avoid this. You can check with this particular example, if you do like that what will happen, okay, this will be avoided, okay. You will have pp also coming into picture, okay, matter will get sorted out. Okay, so that is the pressure velocity decoupling, that is how you avoid non-linearity. Also we can try to avoid it by considering the velocity at the previous time step in this advection term, like I have u into dou u by dou x na. So dou u by dou x, let me consider it at n plus 1, but I will consider u at n time step only. In this way I will avoid the non-linearity. So that is the second challenge which gets avoided. Okay, then what was the other thing? The main thing is the non-availability of an explicit equation for pressure, and for that we have come up with many algorithms. And the most famous, most used algorithm is simple and simpler in almost all the softwares it is used, okay, your simple algorithm, semi implicit method for pressure linked equation. If we get the time at the end of the class I will discuss it, but I would like to sit with it for some time, like it needs some time to explain that algorithm. So maybe I will start in the next class with a simple algorithm how it works, and then we will try to write a code also, okay. So but anyways, so the solution for to get the pressure to avoid that challenge, the explicit equation for pressure, that is overcome using these algorithms where we make use of mass conservation. We solve the pressure correction till the mass conservation is satisfied. So that is the main logic, okay. And this simple algorithm was developed by Professor Suhas Patankar, okay. So he was an Indian who developed this algorithm, and he later on developed another algorithm, simpler algorithm, okay, and most of the commercial softwares do use this algorithm itself, okay. So it was a very big contribution in the field of CFD, okay. So Professor Suhas Patankar, he has written the book also, okay, numerical methods, numerical heat transfers, which is a very kind of standard book which we kind of use for our CFD also. Anyway, so let us get into the questions, the tutorial questions. We will try to wrap it up, okay. And then I will just open the platform for question and answers, okay. Which of the following is a multi-point and implicit scheme? Okay, so there are two things here. I think implicit and explicit I have kind of explained it previously. The only thing addition is the multi-point here, multi-point and implicit scheme. So according to you, what should be the answer for this question? So okay, see, Adam Moulton. Okay, so let us try to see step by step what are these schemes. okay, and which one is multi-point and implicit both. Okay, so let us try to see. So first is the Adams-Bashforth scheme. Okay, so just you need not remember the whole equation here. You just need to remember. You just need to know that. Okay, uh, the while calculating, this is a time advancement scheme. Okay, the Adams-Bashforth scheme. So how we will go from the current time step to the next time step, phi n plus 1. So you are using a trapezoidal rule, I think here. Not exactly trapezoidal rule, a simple uh, averaging of the function at Tn and Tn minus 1. Okay, so remember it is Tn minus 1. So you are using like these are like advection terms. Okay, advection term you are calculating at n, and advection term you are calculating at n minus 1 if you have only advection, if you don't have diffusion. Okay, so that then I am telling okay what will happen. F is nothing but those u into dou u by dou x, those terms. Okay, so that you are calculating at n, and you are calculating at n minus 1 also, and then through that you are calculating the value at n plus 1. Okay, so you can clearly see that it is not implicit because I have never taken n plus 1 at the right hand side. Okay, so this is explicit, purely explicit. That is one thing. Multi-point, now why it is multi-point? Because it is taking the function values, that the advection values at two time steps, n and n minus 1. So that is why it is called as multi-point. Okay, understood? So this is explicit plus multi-point. Okay, now, if we go to Adams-Morton method, okay, there are many Adams-Morton method I think I saw in the literature, but mainly a very simple Adams-Morton method is the one in which you kind of take the average from the current and next time step also, the function at the next time step n plus 1. So the advection term u into dou u by dou x, that you calculate at n plus 1 also. Okay, here, so that is the difference. Okay, so now this becomes implicit, right? Because you are taking at n plus 1, n plus 1, n plus 1 is there here on the right hand side also. So this is implicit. Again, it is multi-point because you are taking the those terms function at n plus 1 and n. So this is multi-point also. So this is implicit multi-point. Okay. Forward time central space. What should it be? Can you write on the chat box? What should be this uh, forward time central space? What should be the nature of this? Like whether it is explicit, implicit, or whether it is, and whether it is a single point or multi-point. Can you write down on the chat box? Explicit, okay. And then single point or multi-point? Yeah, it is single point because we are not taking like two different time levels. Okay, we are just sticking up with this thing. But usually even in a forward time central space, usually we do explicit treatment. That is what I do in my code also, but you can make it implicit also. Okay, the thing is the way in which you calculate this function at say I have considered it at xi. Actually it is not purely implicit and not purely explicit. You can also have something called as crank Nicholson, okay, where it is in between n and n plus 1. So for explicit and implicit it becomes a single point. Okay, so that is the whole thing here. So the answer for this should be anyways Adams Morton, because multi-point and implicit scheme. Okay, the answer is B, not both A and B. It is only B. Okay, Adams Morton. I hope that this is cleared. Okay, any queries with respect to this question? Please write on the chat box. Okay, if there are no questions, okay, we will go to the next question. Which method is not time self starting? Okay, time self starting means um, you can start from initial conditions only. You need only initial conditions to march in time and get the solutions. That is called as time self starting. Now which of the method is not time self starting? Can you write the answer in the chat box? See, these type of questions you can expect them to get in your assignments also. Okay, so that is why we are solving these questions. Okay, and from the exam point of view also these things are important. Okay, but what we have done in coding, that is completely optional, and that is just for your learning purpose. Okay, so what should be the answer for this question? We have just now seen, right, like what is Adams Bashforth. I think it should be just Adams Bashforth. I don't know what is Adams Bashforth. Anyway, it is just Adams Bashforth and Adams Moulton and forward Euler. Okay, we have seen all these things, right? Like just in the previous slide. So for this, what should be the correct answer? Which of the method is not time self-starting? Not is there, not NOT. Okay, I've got one answer, C. Okay, so as I discussed just in the previous slide, Adams Bashforth and Adams Moulton method, both of these are multi-point methods, whereas this forward Euler, it is a single point method. Okay, so a multi-point method will require a solution now at two different time instants to start with. Okay, at least to start with. So it is not time self-starting. Whereas forward Euler, you need only initial condition. You need uh, what do you say, the value, especially if you are doing explicit, you need a value at only one time instant, one previous time instant, and you can start from the initial guess. Okay, so that is why forward Euler is time self-starting. You can start it from the initial conditions. So the correct answer should be both A and B, because these two are multi-point methods and these need two time instant solutions. Okay, so the answer is D here, both A and B, they are correct. Okay, any queries regarding this? I hope that this explanation is satisfactory and you have understood why A and B should be the correct answer. Okay, so let us go to the next question if there are no queries. By reducing the distance between two nodes, we have seen this, right, just now in the code. So it is just a direct question. Okay, I think all of you should be able to answer this because we have seen it in the code only. We have written the code. By reducing the distance between two nodes, that is what we did when we went from 11 to 50 grid points. What happens? The accuracy of the result may increase in quick scheme. What should be the answer? Yeah, as you all of you have said, uh, when we went from n is equal to, okay, here in this weekly content it was from n is equal to 5 to 20. In general, whatever it is, when you increase the grid number of points, this kind of wiggles will disappear and you will get a more smoother solution. So because the Peckley number is decreasing, so that is what I had discussed. Even a central difference scheme will give you a better result. Okay, we had tested it with central difference in the coding part. Okay, not with a quick. I had given quick as a assignment. I mean, you can try yourself. Okay, so there also you will get the same type of nature of solution. Okay, anyway, so that is why true should be the correct answer. You all of you have, I think, written on the chat box. Okay, so first order upwind scheme uses quadratic approximation fit and quick scheme uses linear approximation fit for discretization. Is this true or false? Again, we have, I think, discussed what is first order upwind scheme, how the weights are decided and how the weights are decided for quick scheme. We saw it in last week also and then this week also. Okay, what should be the answer for this question? First order scheme, they are telling it uses quadratic approximation, whereas they are telling quick scheme will use linear approximation. Is that true? Yeah, it should be false, right? Because in first order approximation you are just taking the value of the variable at the phase to be just the upstream point. This is a basic, this is not a quadratic approximation. Quadratic approximation you do it in quick scheme. Okay, that is what I have written here. So the quick scheme itself stands for quadratic interpolation for, I think, convective kinematics. Yeah, something like that. Anyway, you may not remember that. Quadratic is something which you have to know, that phi at the face is calculated as a quadratic equation, ax square plus bx plus c. Fit a and b using these three terms. Okay, a, b and c, sorry, it should be c also. A, b and c using T upstream of upstream, T upstream and T downstream. Okay, this is second order and it uses a quadratic approximation. So quick scheme does not use linear approximation, it should be the other way around. Okay, so this is false, the answer is false. Okay, so next question, can you guys answer? For collocated grids, pressure is stored at dash and velocities are stored at dash. So we have discussed what is a staggered grid and what is collocated grid. Okay, in the last part of our revision section. Okay, we discussed what are the challenges we face when we go with a standard grid, which is also called as collocated grid in technical terms. Okay, we come up with pressure velocity decoupling, and in particular it is called as checkerboard problem also when we use a collocated grid. So what happens in collocated grid? What should be the answer? What do we do in collocated grid? It's the normal grid, right? I mean, which we have been studying like since 2 week contents, whatever previous 2 weeks contents. So in collocated grid, which is our the normal grid, all the variables they are stored at centroid of the control volume only. Okay, all velocities and pressure. So for collocated grid, pressure is also stored at cell center, and then velocity is also stored at cell center. So A should be the correct answer. Okay, yeah. And for a small time step size, higher order method will have higher error than lower order one. Is this true or false? What is meant by a higher order method? First of all, this we had studied in the second week, I think, when we were discussing Taylor series. Okay, we had seen what is this order of accuracy of finite difference scheme. Okay, like central difference, forward difference, backward difference. We had seen the order: first order for forward difference, first order backward difference, and central differences were usually second order scheme. What is the order of scheme? How do you determine that? So that is determined using the truncation error, right? Okay, so the leading terms which we have excluded when we taken when we took that Taylor series, this expansion. So we ignored some terms. Okay, so the leading term of that, it had some order. So delta x raised to n. So that n was our order of accuracy. Okay, so that is what we tell. Even with a time stepping scheme also, the same thing happens. So we have a scheme wherein it will be order of delta t square order of delta t cube, second order, third order, higher order. So with the higher order, what happens? Let us see through this graph. Okay, so this is a standard graph. So whenever you come up with a new scheme, okay, so for example, I had recently developed a fluid structure interaction solver, and I had to determine the time order of accuracy of that particular solver, the fluid structure interaction solver. So what we usually do in research, uh, is that we do calculate the variation of this L2 norm with respect to delta t. Okay, so we run the simulations for different delta t values, ranging from very small delta t values to very high delta t values, for a problem wherein either we know analytical results, wherein we know analytical results. Even if we don't know analytical results, we try to solve the problem at very small delta t and very small mesh, such that we get a very good solution. That is, we consider that as an analytical solution. That is the analytical solution, we consider it. Okay, now we do calculate the solutions at different delta t. Okay, and then we calculate something called as L2 norm of each delta t, for each delta t. Okay, now what is this L2 norm? We kind of uh, sum the errors. Okay, this error is nothing but the whatever value of say velocity I have got minus the analytical velocity, okay, the whole square. Okay, so that is the error square. That is how I calculate the L2 norm. Now I plot this L2 norm with respect to delta t. Now usually what the thing what happens is that, um, if I get L2 norm as something like a delta t square, so the curve will look something like this. Okay, order of delta t square. Okay, what we usually do in when we develop a new solver is that first we plot this. Okay, for delta t square, how should be the graph, and then there will be a third plot also in this. Okay, there will be a third line also in this graph, that will be our for our solver, for different delta t's, how is the variation of L2 norm. Okay, so that also we plot as a third line here, and then we see the slope of that line, it is close to the slope of which order. So for example, if I have a second order scheme, if my whatever I had developed, if it was a second order scheme, then I will get my curve also, which will look similar to this O of delta t square curve. Okay, it will be something like a spline, whereas if it was only a first order accurate in time, I would have got a single linear line. So anyway, so that is the order of accuracy study which we do in research. So usually what happens is that this is how the order of accuracy will vary. This is how the error will vary for different order of accuracy schemes. Okay, so if you go to a very small time step size, which is what is asked in the question, for a small time step size, the L2 norm will be very low. Okay, the error will be very low as compared to order of delta t. Okay, uh, so higher order method should have a less error than the lower order one. Okay, so this is false. Okay, so that should be the correct answer, false, as you have rightly indicated in the chat box. But this is the process which we do in usually in research. Okay, this is how we find out our order of accuracy. Okay, that we have to do these studies whenever we come up with a new solver. Okay, I hope this is understood. Okay, I think I have wrongly mentioned it as true, it should be false only. Okay, which property calculation staggered grid should be avoided? What should be the correct answer for this? Okay, so they are asking for which property calculation the staggered grid should be avoided. I mean, basically what they mean is that for which property calculation you can store the variables at the centroid of the control vector. What should be the answer for this? C. Okay, pressure. Yeah, pressure is correct, but any scalar variable also we can store it at the centroid of the control volume. Okay, so only the velocity we store it at the face of the control volume. Like this x velocity, we store it at this vertical center line, so as to avoid that pressure velocity decoupling. But usually this pressure and temperature, which are the scalar values, we store it at the centroid only. Okay, so we do not use staggered grid for pressure and temperature. So actually both A and C should be correct. Okay, not only C. Okay, so D is the correct answer. That is both option A and C. Okay. Now let us move to the last question. I think this is the last question. Okay. So if the flow is from right to left, which means it is a negative flow. Okay. It is in negative x direction, and we are interested in evaluating the value at phase W. Then at W, then value required at the node is, so phi W is what is required. Okay, so we will try to work it out. So what they are basically telling is that this is W, this is E, this is P, this is W, capital W. Huh? Now the flow is in negative x direction. So what will happen in this case is that our upstreams are little different here. Okay, and we want to calculate what do you say, the value of variable at phase W. Okay, this is W. Okay, so this will be upstream for me now, and this will be upstream of upstream, this will be downstream. Okay, I hope this is understood. This is a bit opposite to what we were usually doing, because we had considered flow in the positive x direction. Okay, so for the phase W, P will be upstream and E will be upstream of upstream, whereas W, capital W, will be downstream. Okay, so usually in the FOU scheme, what we do is that we directly take phi W as phi upstream, which is phi P. Okay, in the central difference, you know, it will be phi at capital W plus phi at capital P divided by 2, right? Capital W divided by 2, phi at W. This is FOU, this is central difference. Now for quick, you need not remember the formula, but it will be just a function of phi at upstream of upstream, that is phi at east, phi at U upstream, that is phi at P, and then phi of downstream, that is phi of capital W. So it will be a function of 3 grid points. Okay, so that's the whole thing. Okay, so as per this discussion, so what we get is pure advection scheme is nothing but first order appoint. I think that is what they want to say. It should be phi at only P. Okay, so only one point is involved, whereas in the central difference, second should correspond to phi at W and P. 2 points are involved. Quick scheme will involve 3 points, so 3 should correspond to 1, 2 should correspond to 3. Okay, 2 should correspond to 3, 3 should correspond to 1, and 1 should correspond to 2. Yeah, so I think the option number this B is correct. Okay, for this. Okay, this is again a repetition of I think previous week this question. For a given figure, if flow direction is from left right, that is U is positive, select the appropriate finite difference interpolation scheme. Here again, how do you select the finite difference interpolation scheme? You need to just to do calculate, you have to calculate the Peclet number. Okay, based on the Peclet number, if it turns out to be greater than 2, you need to go for a uppoint scheme, whereas otherwise you can go with a central difference scheme. Okay, so that is what I have calculated. I think it came out around 250. This we have done in previous week also. Okay, so no problem. This is a repetition. Definitely we have to go with the appoint scheme. Actually, we have to go with a good appoint scheme. First order appoint will not suffice here. We have to go with a, I think actually a second order appoint or quick or something like that. But anyways, in the option, amongst the option, the suitable one is B. Okay, the first order appoint. So you have to answer in this phase also. Whenever something is not available, whatever is closely available, you can mark that. Okay, I hope that this is understood. Okay, so are there any queries? What if it's left right to left? Okay, it would be the same, no problem. The direction does not matter. We are selecting a scheme here, right? Only the thing is the weights would differ. If it is from say right to left, then we will be still using the first order of point, but when we calculate phi at east face, the upstream would be the sorry east face would come here, the upstream would be phi at capital E. Okay, now here it is phi at capital P, uh, if the direction is from left to right. So if I am calculating phi at east face, then upstream will be P. That time, what in your case, that upstream direction will be E. Only that will change. Otherwise, it will remain same. The scheme would remain same. So any queries with regards to today's content? So what we did is, first we kind of saw the performance of convective schemes by writing a simple 1D convection diffusion code, which is an advancement from the previous week's pure diffusion code. So we have taken a one baby step forward. Okay. So we also wrote convection diffusion code, and not only wrote that, we also wrote that for two different convection schemes, first order of point and central difference, and saw in which conditions which scheme will be better, and by increasing the grid size what will happen, sorry, by increasing the number of grid points what would happen. Okay, how the things will change. So that we tried to see. That is one learning which we have to take home. And also what I mentioned is that I'll be uploading this code, and you can try to implement a quick scheme also upon this. That is very easy to add to this code. I have written the code in that way so that it is very easy for you to implement it. Okay, so that you can try to do yourself. Okay, so that is the coding part, and then we got a brief recap of the weekly content, the time advancement, what are the multi-point, single point, explicit, implicit, what are those differences and why we have to consider them. And finally we saw, which is very important, which is like the holy crux of our whole CFD course. This week's content is very important as far as I understand, because you are trying to see the actual Navier-Stokes equation. You are trying to see what are the challenges faced, and to some extent uh, you also have seen what are the ways in which we tackle those solutions, although we will go into deep in the next week. Okay, so we have seen the challenges. So next week we'll see how these challenges are avoided using the algorithm, the simple algorithm, the pressure projection algorithm, and then we will try to implement it. Okay, somewhere. Okay. So any queries? So I'll just stop sharing my screen and then maybe allow you to speak. If there are any queries, you can just, yeah, if there are any queries, you can unmute and ask me. Okay. Yeah, yeah, you can go ahead, Ayaz. Yeah, actually, I have dealt more with simple scheme, but what I understand is that in the simpler scheme, I think the iterative kind of thing which we do in simple method, like the we solve the pressure equation, pressure correction, and then we try to see whether the mass conservation is satisfied or not. So there is an iterative kind of loop. I think that kind of thing is tried to avoid. It is being avoided in simpler by actually solving something called as a pressure poison. But I exactly do not know the details of simpler scheme. It is a simple revised scheme, they call it as. So that the main idea is like that. So we are trying to avoid that. But anyway, I'll get to that in detail in the next week. But what I would say is that these simple schemes, simpler schemes, piezo schemes are also there. But the a very important scheme we I don't know why people miss out is the projection scheme. It is very easy, and we can actually try to solve CFD equations using collocated grid itself, not staggered grid, using collocated grid very easily, using pressure projection scheme. It is like it becomes very easy. Why, I will try to explain it in the next week. We can be using collocated grid because coding becomes very easy with collocated grid as compared to staggered grid, and projection schemes are also very easy. So there you kind of calculate the velocity prediction without using the pressure at previous time step, and then just solve in one go without doing any iterations. You solve the pressure Poisson, and then you come up with the velocity correction. So simpler. I'll try to explain it exact difference next week, but the whole idea is something like that. I As of now I do not know the exact details of that.
So in the projection method, do we ignore any diffusion terms here?
So we do not ignore the diffusion or convective terms in the pressure projection scheme. We do ignore the pressure at the previous pressure gradient term which you find in the momentum equation while calculating the predicted velocity. Okay, u star what you calculate, there we ignore whole together dp by dx, dp by dy. Okay, so that is how we calculate first u star, the predicted velocity. Then we use this information. Okay, so then we apply. So let me just share my screen and then just write it down, because it will be difficult to understand. Okay, okay. So what we do is that first we do calculate u star using un and just the advection and the diffusion terms. We do not include this pressure term altogether. Okay, so then what we tell is that now un plus 1 should be actually u star minus, not minus, it is actually plus, plus what I have ignored. I have ignored the gradient of pressure, right? At again we have to take it at n plus 1 only. So we have ignored this term. Okay, actually delta p by rho, I think we have ignored this term. Okay, whole together. So my un plus 1 should be u star plus what I have ignored while calculating u star. Okay, this is the term I have ignored. So this is how we come up with this equation, and once we come up with this equation, things becomes very easy. So just apply divergence on both the sides, and divergence of un plus 1 is 0 as per the mass conservation, is equal to divergence of u star minus del square Laplacian we get of pressure at n plus 1. Now using this, I think here we get delta t also. Okay, this is u n plus 1 minus u star divided by delta t. So you get delta t whatever is there here, but the concept you have to understand that okay, this is 0. So delta u star I have already calculated it here. Okay, in the first step I solve this Laplacian equation to directly calculate pressure at n plus 1 because I already know u star. So direct I am getting pressure at n plus 1 without doing anything. Okay, so then I just substitute this back into this equation, and then I get un plus 1. This is like a two-step procedure. No, three-step procedure. Okay, direct you are getting un plus 1 and pn plus 1. So this is as simple as that. It's a very simple method. I don't know why people don't use it much, but in my code I personally use projection methods, and it has performed quite very well. And next week I'll tell why we can use collocated grid also for this. We need not use staggered grid also here. We'll be altogether avoiding pressure velocity decoupling. Is this understood, this pressure projection algorithm?
Yes, sir.
Yeah. So this is the way in which we do. We do not ignore any viscous terms, and those things we consider while calculating U star. Okay. Any other queries?
So in for back algorithm,
Huh.
like initial guess value we do for pressure and force.
Yeah, we take it from previous time step, I think. No?
So do we ignore the unsteady term? We take
Unsteady terms of what? Momentum. Unsteady terms
like,
of.
like math is not clear to me. See, I didn't went through very well in the last week.
Yeah, the content was a bit very high. So yeah. So what I was planning is, let us try to cover these things in the beginning of next week, because again these things will be continued, the practical implementation of that. So Mac is one thing, simple is one thing, and pressure projection, I would mainly concentrate on pressure projection. The Mac thing, there we use the some concepts of pseudo compressibility or something like that. So once we do calculate U star and all, we write it in terms of like the mass conservation equation, we put it, then we calculate the residual term. Okay, so and then we kind of put it back into the our momentum equations, whatever residual terms is there. So but as you said, for uh, unsteady cases, it might not be very useful, and that is why we usually do it for lead driven cavity problems, which kind of reach a steady state or something like that. Okay, but that is not again mostly used algorithm in CFD, the Mac algorithm. It is again very simple to, I think, compute. We can do it with a collocated grid also, the Mac algorithm. We can do that. We do not require staggered grid. uh, but I think that is the limitation, and we usually go for simple or pressure projection. But I'll deal with these solution algorithms mainly in detail in the next class. So that is what I had planned, because otherwise this will become too heavy kind of content. Yeah.
Okay.
Yeah. Any other queries? If there are no queries, yeah, thank you for attending the class. So we will meet next week, and we will start with mainly these algorithms, the way in which they work. The Mac algorithm I will explain in brief, and then we'll go to simple algorithm, and then we will see pressure projection, and then we will write a code using pressure projection. So that is what I have thought of, because you will see that pressure projection is easy to write code also. Okay. Yeah, thank you. Yeah, thanks for that. So if you have any feedback, please write to me also. Okay, you can write to me on this mail ID. I will just share this. You can write to me on this. It would be great to hear from you your feedback. Okay, so I'll just keep that in mind while conducting the future classes. Okay. Yeah, thanks for attending. Okay.
Thank you, sir.
Okay. Bye.